Hey there, awesome physics students. Let's talk about fluid flow rate. Now, in general, it's going to take a pressure difference between two ends of a pipe, for example, to cause fluid to flow from one end to the other. Now, I don't want to talk about the pressure difference right now. I want to talk about the flow rate. The flow rate is the amount or the volume of fluid flowing through the pipe or past a certain point per time interval. We usually use the letter Q for that, and the flow rate is just the volume that's passing a particular point per time interval. So in SI units, this is going to have units of something like meters cubed per second. Of course, that's a terrible unit because a cubic meter is enormous and it's not very intuitive. A better unit is something like liters per second, right? Or even gallons per minute is pretty intuitive. If you have a shower head, oftentimes they'll list the flow rate on the shower head itself in gallons per minute. So that's telling you how many gallons are coming through the shower head every minute. And the flow rate here, that is a flow rate. It's just not perhaps in the units that we would always want. We want to understand how that flow rate affects the fluid as it flows through different pipes. So let's think about a scenario here where we have fluid flowing through a pipe. And I want to consider so let's say the flow velocity of the individual particles is v1 this way. I want to think about what happens to a chunk of volume of size v1 at this point here. Now this volume, I'm going to take a sort of a cylindrical slice of this, and that slice is going to have width of delta x1, and the area of this is going to be a1. So as it moves through here, let's say we do something interesting, like we narrow the pipe and we let it become a lot thinner. Well, what happens to this fluid as it travels along this direction? Well, if I'm going to take this fluid here and I'm going to say it's incompressible, that is that I can't squish it to reduce the volume. In other words, the volume here is going to be the volume here. The volume stays constant. Then in order to squeeze this volume here, I'm going to have to spread it out because the area here is going to be a lot smaller, right? The area 2 is a lot smaller than area 1. And so when I do that, I'm going to have to spread it over a longer delta x. And so this is going to be my delta x2, this width here. And then this is going to have some velocity v2 through the pipe. So I want to relate these things to each other. Now, one key thing that I know you may have noticed that I said is that the volume has to be the same in both spots. So if the volume is the same, I'm saying that the volume can't decrease or increase. In other words, whatever comes in has to come out. It doesn't go anywhere else. There's nowhere else for it to go. That's what we call continuity, or it's continuous. Let's just relate these things. The volume here is just going to be the width of this, that's delta x1, times the area, a1. And same for this volume here, v2, and this is a volume different than velocity. I write my volumes with no little sideways garnish. My velocities always have this little flat, little sideways garnish there. The volume here is going to be delta x2 times the area here. Now, I really want to know about the volume flow rate. So Q is going to be just the volume flow rate. That's just either of these volumes divided by the time interval, right? So so I can take this one. That's going to be delta x1 times a1 over the time interval. Or we already said these two are equal, right? So I could set that equal to delta x2 a2 over delta t. Okay. Now let's look and see what we got here. This here looks just like a velocity. And in fact, that's this velocity, right? So we're saying that v1 times a1 is equal to, now again, this here looks just like this velocity. That's v2 a2. And the whole thing, this whole thing is a physically meaningful quantity, that is the flow rate, the number of the amount of fluid passing a point per time. Notice though that I should probably write this a little differently. The velocity here is rather small, but the area is pretty big. But because the flow rate is staying the same, that is, whatever comes in has to come out, whenever it comes out the other side, I'm shrinking this area, so the area is shrinking. But that means the velocity, v2, has to be big. So it actually speeds up as it comes in here. Now this is a little counterintuitive. If this were traffic in cars, we're saying that as 6 lanes goes down to 2 lanes, the cars speed up. Well, cars are not an incompressible fluid. They are compressible. The distance between cars changes as you speed up or slow down. Here we're saying the distance between the molecules doesn't change. The volume of that chunk doesn't change. Okay, and that is a unique circumstance for it's not something we have good intuition about. And so because whatever comes in has to go out, the velocity has to speed up because it's squished into this smaller area. And you see this if you look at faucets, right? If you have a faucet and it has water flowing down, as the water comes down out the tip, you'll see it narrow as it falls. It's because as it falls, the velocity the velocity increases, so the area decreases because it's the same volume flow rate. Up here the velocity is rather small, but the area is rather big. Okay, so this hopefully explains what you've seen at faucets. All right.